one of the last, that's how I'm feeling. Okay, one of the last bonding videos that we're going to be doing, all the forces. Okay, so there are two different types of forces, and these are intermolecular forces. Intermolecular forces are forces between molecules. We haven't talked about intermolecular forces yet because these are hella weak forces. We've only talked about forces kind of in a roundabout way called intramolecular forces, and they're forces that are inside a molecule. And those are very, very strong. So that's like the shared electron. A covalent bond is an intramolecular force. Ionic bond is an intramolecular force. So we have to talk about all the different types of forces in the video today and how that relates to keeping a molecule together. Now, the first three we're going to look at are the really weak forces, the intermolecular forces. Now, the best way to describe an intermolecular force is inside a molecule, this bond right here, this is very strong because it's keeping the hydrogen next to the carbon. Look at these guys. They're in love. Very strong attraction. Look at that. Okay. Now, what happens that's intra. What happens in intermolecular bonds is that this carbon has protons, right? We don't show it, but it's got 6 protons. And those protons, while they're happy with this relationship, they might check out the electrons that are over here. They might look over there and go, ooh, just a little check out, just a little flirty, like look away, check it out. And then they look away. You take a peek and then you look away. So it's a little flirty glance. And then it's like, woo, he's a hottie, those electrons. But then you're like, oh wait, no, I'm in a committed relationship. Attraction. Strong. Okay. So this picture is not true because of the angle, but this is good. Here we go. All right. So we have Obama and we have President Macron. Who's he attracted to? But it's actually, she's like way further up. Otherwise, she would be this really tall person. Anyways, that's flirty glance. So the first force is something called London forces. And the way to think about a London force is think about bodybuilders. The more mass you have, the stronger you are. And that's literally the fastest and easiest way for me to explain the weakest force in all of chemistry that has to do with bonding, and that is London forces. What is it? Basically, it's the attraction of one proton in one molecule for the electrons in another molecule. That's all it is. And everything has London forces. You, me, trees, slugs, bugs. Everything has London forces. And they scale with molar mass. The more protons you have, the heavier you are, and the more your protons are slightly attracted to other molecules' electrons. So the example is that even though hydrogen has an attraction to the shared electrons over here, this might be a little bit attracted to the electron over there. And this goes way up. If you have iodine has 53 protons. And that's why iodine is a solid and fluorine is a gas. Fluorine has very, very weak London forces, but iodine, due to its mass, has incredible attraction for other iodine's protons, and that keeps it together as a solid instead of a gas. So when in doubt, add up the protons. The most protons win. Okay. The second type of intermolecular force is something called a dipole-dipole force. Now, I had a chem teacher who was also our physics teacher in my high school, and he was a Scottish guy, and he was super old school. So he didn't give notes like I'm giving to you. He just talked, and you had to like write stuff down. He didn't write anything on the board. It was crazy. It was really hard to wrap my head around it. And because of his thick accent, there were two things I got wrong in physics and chemistry. I thought he wasn't saying dipole. I thought he was saying diaper. So I was writing like diaper forces. I was like, maybe the guy's called diaper? I didn't get it. So, but it's actually dipole forces. The other word I didn't get was elevator in physics because he had all these elevator problems. But with his accent, I thought he was saying alligator. So in my physics notebook, I was drawing like alligators going up at different speeds. I was like, why are they moving up and down? I don't get this. Why? I thought he was being whimsical, but he was actually just saying elevator. Anyways, so London dispersion is here. Dipole forces are here. Dipole forces are way stronger. You automatically have dipole forces if the molecule is polar. So, for example, oxygen with two bromines around it in a bent shape, these are going to be going into the oxygen because oxygen has a higher electronegativity. We have an overall arrow going up. That means the top is negative and the bottom is positive. So this was in the previous lessons, right? That means this has London dispersion because everything does, and diaper forces. Now, Cl4, if you were watching the other video, good chance this is a tetrahedral, and it is. And if we draw all the little dipole arrows going out, they're all going away from each other. So there is no polarity here. This has London dispersion, but no dipole forces. Dipole forces are magnitude stronger than London dispersion. And that may explain why something like water, which is polar, right? If we draw our arrows right, because they're going to be pulled into the oxygen, and water only has 10 protons. Chlorine is a gas, water is a liquid, and chlorine has 34 protons. So dipole forces and elements, molecules polarity automatically makes it stronger. There is the strongest intermolecular force, and that's called hydrogen bonding. It's a special type of dipole bonding. It's like dipole on steroids. And there are three combinations you have to remember. If a hydrogen is directly attached to a fluorine, it is hydrogen bonded. It just means it's got a very strong dipole force. It just means that there's a big difference in electronegativity. Hydrogen's 2.2, fluorine is 4, so we've got a 1.8 difference. This is a big difference in electronegativity. It means one side is really, really negative. The other thing is if you have an OH or NH bond. Now, this looks like it has hydrogen bonding, but when we draw it out, we do not have a hydrogen directly attached to a fluorine. Oh, you have to have that. The fluorine is actually attached to the carbon. Here we have ammonia, and when we draw this as a pyramid, it's polar, but it's also got hydrogen bonding. Water also has hydrogen bonding because of the OH bond. So we've got London dispersion over here, dipole over here, and hydrogen bonding right here. So hydrogen bonding is really, really strong. The irony is those three intermolecular forces pale in comparison to the next type of forces, intermolecular forces, because we're going to be talking about ionic. That's how far apart they are. Metallic. And then if I was to draw something in Mr. Zielinski's class, that's where network covalent would be. Okay, so recap. London dispersion is like a minion. One minion by itself is basically useless, right? They're garbage. You can't even if you get 4 of them together, they basically can't even babysit kids. But if you get a ton of minions, they actually can help you become a supervillain and make great gadgetry in your basement. Also, they run on bananas. Okay. Dipole bonds, think of like a magnetic power. Woo! So if you have two different poles like a magnet, it's very strong. Then we have hydrogen bonds. Now, I'm going to have a link to this video in the lesson today. This is something you should watch. A hydrogen bond is Jackie Chan. Because Jackie Chan can beat 10 bosses and about 100 goons. So that's Jackie Chan is like a hydrogen bond. He's just a really strong dipole force, but you can just lay waste to goons. So make sure you watch this video. Okay, real quick. Oh, yeah. Here we go. Since we're talking about martial artists, we have Steven Seagal as London Dispersion. He's terrible. Then we got Jean-Claude Van Damme. And then, Jackie Chan. This guy's amazing. Love Jackie Chan. Okay. Bruce Lee is network covalent. We're going to talk about network covalent in a second. Okay. So ionic forces are the first intramolecular force. Intramolecular force. And it's between a metal and a non-metal, obviously. This is hundreds of times stronger than hydrogen bonding. The reason why is that there is such a difference between electronegativity that the metal loses its electrons to the non-metal, and you get a positive ion and a negative ion. So you basically get one huge positive ion and one huge negative ion, and there is some crazy attraction between those. Okay? So when salt water is broken apart, it's broken apart because it's also soluble because of that rule. Because it's got a positive and negative ion, and because water has positive and negative ends, right? Water has a negative end near the oxygen, but it also has a positive end near the water, the hydrogen end. It actually gets surrounded. So, like here, I'll infinite clone this. Let's see if this is going to work. Okay. Infinite clone. Perfect. Okay. So basically, the water, based on the orientation, surrounds... Nope. There we go. It surrounds the ions. So because ionic compounds have charges, they are surrounded by polar molecules and thus dissolve. If you are not polar, then you are not surrounded by those same molecules. After ionic compounds, we have metallic forces. And those are just metals. That's it. Like cobalt. Anything to the left of the staircase, when it's by itself, has metallic forces. That's why all metals, with the exception of mercury, are solid at room temperature. Even something with an incredibly low amount of protons like lithium. Lithium has 3 protons. That's it. Lithium is not polar. Lithium has no hydrogen bonding. Lithium is not ionic, but it's got metallic forces. Now, why are metallic forces so strong? Because metals have such a low electronegativity, their affinity for electrons is really low. It causes the electrons to wander away, and you get a sea of electrons surrounding the atoms. That allows every atom to basically be sort of attracted to random electrons that flit into its attraction domain. That's very complicated, but it's basically like if you ever grew up in rural Alberta, it's like these are kids in the summer that run around town, and everybody just kind of looks out for them. Like, you know, this is Jimmy's mom right here, but Jimmy's like way over here. Now, Jimmy's mom loves Jimmy, but she's busy. It's a good thing that Bill's there, because Bill is watching Jimmy, and Bill is actually dad to Susie, who's over here. So they just kind of like spread out, but everybody's watching everybody's back, right? So that's metallic ions. And the last force of all of and the strongest is something called network covalent. There are only two that do this. Well, IBs, we're going to talk more about this on Monday. That's carbon and silicon. And they exist in a 3D lattice that repeats itself over and over and over again. Silicon dioxide is one other one, silicon carbide. So here are the four that you have to know. All of these exist in a network covalent system because carbon has, and silicon has, 4 valence electrons. So what you get is carbon binding itself in 3-dimensional space to infinity and beyond. So you know how we drew this? What if instead of having a hydrogen at the end, you have another carbon, and then that just continues forever? It's kind of fun, actually. And then that might go back. So you have carbons that in this massive chain. Silicon's the same thing. Silicon dioxide, I'm gonna talk about this with the IBs on Monday. It's a little different. Network covalent produces 3 things you've probably heard of before: diamonds, sand, and graphite. I'm going to have some more links about graphite in the lesson today. So, but anyways, that's it. I did that really fast. So you might have to rewind this. And there is a question in the notes, or there's a question in your assignment that you have to do this for. So I kind of was rushing because it's a big, long spiel. That's the lesson for today, and it's Friday. Yay!